Hey guys, I'm back with your 7.1 day 2 notes. So today's notes are all going to be about the inverse cosine function and what angles and ratios survived the cut of his graph to make his inverse exist, okay? So before we do the inverse cosine, let's just review what we did before, and that was the sine. So the original sine function, y equals sine x, right? The original sine function, you plug an angle in as x, and you get a ratio of two side lengths out. That's how the original sine function worked, right? So angles went in your domain, which were all real angles. You could take the sine or cosine of any real angle. And then the range, ratios only between -1 and 1 came out, okay? Perfect. Your range were those ratios, okay? And it had to be something in between -1 and 1. All right, then we did the inverse sine. The inverse sine, though, has to undo the sine function. So now you plug a ratio into the inverse, and the inverse spits out an angle. All right, so your ratios go in as your domain, and only ratios between -1 and 1 survived the cut, so all the ratios from the original function survived. And then, but the angles that are now able to come out, the angles that survived his cut were only angles between -pi/2 and pi/2. Those are the only angles that an inverse sine function will ever be able to spit out, okay? All right, so the inverse sine can only spit out angles between -pi/2 and pi/2. So right now, when you're answering questions, you don't ever want to say that the answer to an inverse sine question is anything other than an angle between -pi/2 and pi/2. Okay, right now, the cheat chart, right? We saw that if you take the inverse sine of a positive ratio between 0 and 1, it's going to spit out a quadrant 1 angle. You know that, all right? If you take the inverse sine of a negative ratio between 0 and -1, it's going to spit out a quadrant 4 angle between 0 and -pi/2. That's how the inverse sine function works. So I find myself drawing this picture a lot. You have your unit circle. We have pi/2. We have -pi/2, right? At the point 0, 1, and the point 0, -1. You have 0 radians in between at the point 1, 0. Okay, and it's only going to be able to spit out the inverse sine. This is for the inverse sine. He's only going to be able to spit out these angles from -pi/2 to pi/2. So only these angles could ever come out, and only these ratios could ever go in, okay? All right, perfect. All right, I'm going to skip this part. It's just, again, leading into the inverse cosine. Well, before we can work with the inverse cosine, first we have to look at the graph of cosine and see what portion of his graph we kept to make the inverse cosine exist, okay? So again, I went ahead and I took the graph of y equals cosine x, and I graphed it for us, just so we could have a little bit of less time on the video. All right, so I plugged all these all these angles into the cosine, and I got all these ratios out. He had an original domain of any angle could go in, and a ratio between -1 and 1 come out for the cosine. So here is the graph of your cosine function, right? And it's easy to see that this function is not 1-to-1. The y values are clearly repeating themselves after so many inputs. So it's not a 1-to-1 function, and it shouldn't have an inverse. It can only have an inverse if we start to chop its graph, okay? Well, where does the cosine get chopped? What portion of the graph did we keep? So again, it makes sense to start right at 0, right, the beginning of his graph, and then try to get one cohesive piece of his graph that passes the HLT. So if I start at 0 and I start checking, does this pass the HLT? Yes, 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 yes. Well, you know what? Let me back up first. First of all, the way the cosine graph works, right? Right now it's saying if you plug an angle between 0 and pi/2 in, then a ratio between 1 and 0 comes out. So these are all of your quadrant 1 angles and ratios that live on this leg of the graph, right? Then it says, according to his graph, if you plug an angle between pi/2 and pi into the cosine function, then a ratio between 0 and -1 come out, right? That's what this leg of the graph says. And those are all of your quadrant 2 angles and ratios. Then his graph says, if you plug an angle between pi and 3 pi over 2 in, if you plug any one of these angles in, then a ratio between -1 and 0 will come out of that function. So that's your quadrant 3. Angles and ratios that live on that leg of the graph. All right, and then the graph says if you plug an angle between 3 pi over 2 and 2 pi in, right on this leg, then a ratio between 0 and 1 will come out. So these are all of your quadrant 4 angles and ratios. And then it will repeat. These are quadrant 1 again, quadrant 2, quadrant 3, quadrant 4, and so on. And I can even go back here, right? If I plug an angle between 0 and -pi over 2 in, then according to the graph, a ratio between 1 and 0 will come out. So those are your quadrant 4 angles and ratios. Okay, and so on. So now we can go. So if I want to start chopping his graph to get one cohesive strip that passes the HLT, right, to make it 1 to 1. Well, let's start at 0. Does this pass the HLT? Yes, 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 yes. But the minute I make this turn, it will no longer continue to pass the HLT. So I have to chop the graph right here at pi. Okay, so now if I want to go back, I started at 0 to go back this way. The problem is if I start to go back, he won't pass the HLT anymore, which means I can't go past him. So I'm going to have to chop it right there at 0. So the only portion of the cosine function graph that survives the cut is from 0 to pi. That is the portion of the cosine graph that we keep to make his inverse exist. This right now is a 1 to 1 function with just this piece of his graph. So if you notice, only quadrant 1 and quadrant 2 angles and ratios survive the cut of his graph. Okay, so that's what we're going to keep for the inverse cosine function to exist. We're going to keep this portion of the cosine's graph. So again, it's going to go from 0 to pi, that survived the cut, and ratios from -1 to 1 survived the cut. That is what we do. Okay, so now let's go on the back. So now we see, therefore, the inverse cosine function only exists for angles in between 0 and pi, because those are the angles that we kept to make his graph 1 to 1 and have an inverse. Angles from 0 to pi. Okay, so, and those are going to be angles that are found in quadrant 1 and quadrant 2. Okay, all right, so here we go. So the inverse cosine, right? So now we're going to plug a ratio in and get an angle out. But he's only going to be able to spit out angles between 0 and pi. So the domain. Well, what ratios are we allowed to plug in? Well, what ratios survived? The ratios that survived were the ratios between -1 and 1. All right, so all the ratios survived. So his domain, which are your ratios, are going to be from -1 to 1. Okay, and then his range, what angles is he going to be able to spit out? Well, only angles between 0 and pi. Those are the only angles that survived the cut. So those are going to be the only angles that is going to be physically capable of spitting out. So his range is going to be from 0 to pi. Those are the angles that exist. Okay, all right, so if I go to graph the inverse cosine, right? Now we're going to plug ratios in as the x's. So it's going to be ratios from 1 to -1 that survived. And then it's the angles that are going to come out of this inverse function. And only angles from 0 to pi exist. Okay, all right, perfect. So now if I go back, and then again, halfway in between 0 and pi is pi over 2. Okay, so now if you go back and you grab points, right? Well, if the point 0, 1, oh, am I on the graph? If the point 0, 1 is on the original function, then 1, 0 is on the inverse. So now, when I plug a ratio of 1 in, an angle of 0 comes out. Okay, now I go back, grab another point. Well, right here, the point pi over 4, root 2 over 2. So if the point pi over 4, root 2 over 2 is on the original graph, well then root 2 over 2, pi over 4 is on the inverse's graph. So now a ratio of pi over 2, which is like 0.7, not pi over 2, root 2 over 2. If a ratio of root 2 over 2 goes in, then an angle of pi over 4, which is half of 90, which is 45, comes out. Okay, all right, go back, grab another point. If the point pi over 2, 0 is on the original function's graph, well then 0, pi over 2 is on the inverse's graph. So now 0 goes in and an angle of pi over 2 comes out. All right, go back. Grab another point. Well, the point 3 pi over 4 root 2 over 2. An angle of 3 pi over 4 goes in, and a ratio of negative root 2 over 2 comes out. So then that means on the inverse, when a ratio of negative root 2 over 2 goes in, then an angle of 3 pi over 4 comes out. So now when negative root 2 over 2 goes into the inverse, negative 0.7-ish, then the angle 3 pi over 4 comes out. Okay, think of this as 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi's over 4, if you will. All right, and then the last point that survived the cut of his graph is right here. When pi radians went in, a ratio of negative 1 came out. So now, when a ratio of negative 1 goes in, an angle of pi radians will come out of the inverse. All right, so a ratio of negative 1 goes in, and an angle of pi radians comes out. So now, this is what the graph of the inverse cosine function looks like, okay? So look at what it says. It says that if you plug a ratio, well, let's do it down here, I have it written down. If I plug a ratio between 0 and 1 in, if I plug a positive ratio between 0 and 1 into this function, then an angle between 0 and pi over 2 comes out. You see that? If I plug any of these ratios in, then any one of these angles that lives on this leg of the graph between 0 and pi over 2 can come out. Okay, so again, if I plug a ratio between 0 and 1 in, then an angle between 0 and pi over 2 comes out. That's a quadrant 1 angle. So if you take the inverse cosine of a positive ratio, an angle in quadrant 1 will come out. Okay, and therefore, if you ever have to draw a picture, you want to put that angle or put that triangle in quadrant 1, because that's where that angle would have been when you take the inverse cosine of a ratio between 0 and 1. All right, now the graph says this. If I plug a ratio between 0 and negative 1 in, if I plug any of these ratios in to the inverse cosine, then an angle between pi over 2 and pi comes out. One of these angles now comes out. So if I plug any of these ratios in, now an angle from here to here comes out. So that means an angle between pi over 2 and pi will come out. And where are angles between pi over 2 and pi found? Those are quadrant 2 angles. All right, so if you ever take the inverse cosine of a negative ratio between 0 and negative 1, it's going to tell you the answer is an angle between pi over 2 and pi, a quadrant 2 angle. So then if you ever have to draw a picture, put that triangle or put that angle in quadrant 2, because that's where it would have been, okay? All right, so remember, only quadrant 1 and quadrant 2 angles survive the cut of his graph. So he's only going to be capable of spitting out quadrant 1 and quadrant 2 angles, angles between 0 and pi. That's how the inverse cosine works, okay? So the inverse cosine can only spit out angles between 0 and 180 degrees, if you're thinking of it in degrees, or 0 and pi radians. That's the only angles he'll be able to spit out, quadrant 1 or quadrant 2 angles. And we saw that if you take the inverse cosine of a positive ratio, it's a quadrant 1 angle. If you take the inverse cosine of a negative ratio, it's a quadrant 2 angle. But just make sure that ratio is always in between 0 and 1 or 0 and negative 1. All right, let's practice some examples. Okay, so let's say you have to find the exact value of, right? What is the inverse cosine of 0? Okay, now again, your zeros, your ones, your negative ones, those are usually special ratios for your quadrantal angles, right? Your zeros, your pi's over 2, your pi, and whatnot. So again, right now we're trying to figure out what angle this equals, because when you take the inverse cosine of a ratio, the answer is an angle, right? Well, remember, the inverse cosine is only able to spit out angles between 0 and pi, quadrant 1 and quadrant 2 angles. So you're trying to figure out the angle between 0 and pi that makes this statement true. So I kind of flip it around. I say to myself, okay, well, the cosine of what original angle would have had a ratio of 0? Okay, well, guys, think about it. Right here, you have these quadrantal angles. You have 0, pi over 2, and pi. And you have the ordered pairs 1, 0, 0, 1, and negative 1, 0. The cosine of which one of these angles had a ratio of 0? Remember, cosine was the x-coordinate. Who has an x-coordinate of 0? Pi over 2. It is the cosine of pi over 2 who would have had a ratio of 0. So the answer to this question is pi over 2. That is the angle that makes this true. And again, if you use a calculator, if you ask your calculator, if you're in radians, what is the inverse cosine of 0? It probably says to you 1.57 something, because that's what 3.14 divided by 2 is. It's 1.57 something radians, okay? So it gives you the estimated decimal answer, not the exact angle answer, like pi over 2, okay? But again, if you went to your cheat sheet and you were looking at inverse cosine, the cosine of what angle had a ratio of 0? Right here, it's pi over 2. That would have been the angle that you wanted, okay? All right, let's try another one. Now again, normally when they ask you these ones to find the exact value, your angle has to be special. It's got to be a quadrantal like 0, pi over 2, pi, or it's got to be a pi over 6, pi over 3, pi over 4, or some multiple of them, okay? All right, this one says the inverse cosine of negative root 2 over 2. Okay, well, root 2 over 2 is like 0.7. So that's a ratio between negative 1 and 1. So he's good. So guys, you're taking the inverse cosine of a negative ratio. We know that if you take the inverse cosine of a negative ratio, it's going to spit out an angle in quadrant 2. So we know the answer to this is some quadrant 2 angle. Okay, so then I kind of turn it around. Remember, he can only spit out angles between 0 and pi. Quadrant 1 or quadrant 2 angles. So what quadrant 2 angle makes this statement true? So I turn it around into the cosine of what quadrant 2 angle equaled a ratio of negative root 2 over 2. Okay, well, again, the cosine of what special angle was root 2 over 2? The cosine of what special angle had a ratio of root 2 over 2? It's a pi over 4, right? So I know it's some version of pi over 4. The problem is the answer can't be 1 pi over 4 because 1 pi over 4 lands in quadrant 1. I need the multiple of pi over 4 that landed in quadrant 2. So if this is the world of pi's over 4, this is 4 pi over 4. So what angle landed in the quadrant right before him that is a multiple of pi over 4? 3 pi over 4. So the answer is 3 pi over 4. That is the angle that would have had a cosine ratio of negative root 2 over 2. And again, if you ask your calculator, it'll give you the decimal version of him, as long as you're in radians, okay? Now again, you can use your unit circle. Just look for the quadrant 2 angle that had a cosine x-coordinate of negative root 2 over 2. I'm telling you, it's 3 pi over 4. All right, last one over here. Oh, no, sorry, not last one. What if they asked you, what is the inverse cosine of root 3 over 2? Well, root 3 over 2 is about 0.86. So he's definitely a ratio between 0 and 1. So he's a good ratio. So guys, look at what they're saying. When you take the inverse cosine of a positive ratio, we know the answer to that is going to be a quadrant 1 angle. I already know this is a quadrant 1 angle. So I turn the problem around. The cosine of what quadrant 1 angle would have had a ratio of root 3 over 2? Well, do you remember the cosine of what special ratio? 30, 45, 60. The cosine of what special angle? 30, 60, 45 had a ratio of root 3 over 2. So if you go to your cosines, who had a ratio of root 3 over 2? It's pi over 6. And since he needs to be a quadrant 1 angle, that is pi over 6. And again, if you ask your calculator, it gives you the decimal version of pi divided by 6 because that is the angle that makes this statement true. All right, look here. The inverse cosine of negative 1/2. Well, we know if we take the inverse cosine of a negative ratio, it's going to spit out a quadrant 2 angle. So we already know the answer to this is some quadrant 2 angle. So let's turn the problem around. The cosine of what quadrant 2 angle would have equaled a ratio of negative 1/2? Well, guys, think about it. The cosine of what special angle? 30, 45, 60, who had a ratio of 1/2? So we look over here, who had a ratio of 1/2? It's pi over 3, right? However, pi over 3, he lands in quadrant 1. I need some multiple of pi over 3 that landed in quadrant 2. The answer to this has to be a quadrant 2 angle because the ratio is negative. So in the world of pi's over 3, here's 3 pi over 3. So what pi over 3 is this that came right before him? 2 pi over 3. It must have been 2 pi over 3 radians that had a ratio, a cosine ratio of negative 1/2. All right, now again, you could also go to your unit circle and look for the angle in quadrant 2 who had a cosine in x coordinate of negative 1/2. And I'm telling you, it's going to be 2 pi over 3. Okay, all right, so that's how we use it in that regard. Now they want you to find the exact value of. So these are meant to be extremely, extremely simple unless they try to trick you, okay? So look here, find the exact value. The cosine and the inverse cosine, they are inverse functions, guys. They should cancel each other out, so it should be easy, all right? So essentially, oh, I forgot a parenthesis. Eventually it says the inverse cosine of the cosine of pi over 12. Well, if you break this problem down, we would do in parentheses first, right? The cosine of this angle would be a ratio. Then you would take the inverse cosine of that ratio and your final answer would be an angle. So the answer to this question should be an angle. Well, guys, what does the inverse cosine and the cosine function do to each other? They should cancel each other out and you should be left with this angle. And as long as pi over 12 is an angle that the inverse cosine function is capable of spitting out, you keep him, you're done. Is pi over 12 an angle who lands between 0 and pi? Well, guys, a way to test that, if this is pi over 2, then in the world of pi's over 12, well, I have to times 2 by 6 to get to 12, so times the top by 6. That's 6 pi's over 12. So if this is 6 pi over 12, guess where 1 pi over 12 lands? In quadrant 1. So he's definitely an angle that the inverse cosine would have been capable of spitting out. So pi over 12 is your answer. Okay? All right, look here. What is the inverse cosine of the cosine? I forgot to pronounce it again. What is the inverse cosine of the cosine of negative 2 pi over 3? Well, remember, if you took the cosine of an angle, the answer would be a ratio. When you take the inverse cosine of that ratio, the answer would be an angle. So the final answer should be an angle. So what should the inverse cosine and the cosine do to each other? Cancel, and you should be left with this angle. But here's the problem. The inverse cosine would only be able to give you an answer between 0 and pi radians, all right? Does anybody know where negative 2 pi over 3 radians land? Well, think about it. Negative, we got to go this way. So negative 2 pi over 3, here's pi, so that's negative 3 pi over 3. Ooh. All right, so negative 2 pi over 3, he lands in quadrant 3. Would the answer to an inverse cosine function ever be a quadrant 3 angle? No, because he's not capable of spitting out quadrant 3 angles. So here's the problem. You have to turn this angle into an angle that he would have been capable to spit out. So this is where I go to this guy. You know how all students take calculus? So all ratios are positive. Students means that the sign is positive, but it means the cosine is negative, right? And then take means the tangent is positive, which means the cosine is negative. And then calculus means that the cosine is positive. So right now, negative 2 pi over 3 is a quadrant 3 angle. He's here. So you have to turn him into an angle that is in either quadrant 1 or quadrant 2. Well, where else is the cosine ratio going to be negative? In quadrant 2 or quadrant 1? In quadrant 2. So you have to move him to his equivalent quadrant. So I have to turn negative 2 pi over 3 into a quadrant 2 angle. So let's just use the reference angle. Negative 2 pi over 3 has a reference of pi over 3, right? So now what angle lands in quadrant 2 that is a multiple of pi over 3? Well, guys, if this is 3 pi over 3, then the one that fell right behind for him is 2 pi over 3. So the answer to this question is positive 2 pi over 3. Okay? Now, let's pretend this was a quadrant 4 angle. Well, again, he couldn't have spit it out. If it was a quadrant 4 angle, well, then his equivalent would be to move it to quadrant 1, where it's positive again. All right, so you just go to the matching quadrant, and you turn it into an angle that he would be capable of spitting out. And he can spit out 2 pi over 3, because that's between 0 and pi. I know those ones are a little bit tricky, okay? But this is really, really helpful. All right, look here. What if it asks you to take the cosine of the inverse cosine of 1.5? Well, guys, remember, let's take this problem. Let's digest it. If you take the inverse cosine of a ratio, the answer is an angle. When you take the cosine of that angle, the answer is a ratio. So the answer to this should be a ratio. And now what should the cosine and the inverse cosine do to each other? They should cancel, and you should be left with that ratio as your answer. But here's the problem. Could the cosine function ever spit out a ratio of 1.5, something bigger than 1? Or would you ever be allowed to plug a ratio bigger than 1 into the inverse cosine function? No. So this is actually a trick. This is a ratio that doesn't apply to the cosine or inverse cosine function. So the answer is undefined. If you plug that into your calculator, it would literally tell you like domain error or undefined. All right, last one. If I want to know what is the cosine of the inverse cosine of negative 3/4, right? Well, just digest it. If I took the inverse cosine of that ratio, the answer is an angle. When I take the cosine of that angle, the answer is a ratio. So the overall answer should be a ratio. So what should the cosine and the inverse cosine do to each other? It should cancel. And now this should be your answer, this ratio. And as long as that is a ratio between -1 and 1, you're golden. And is that in between -1 and 1? Yes. So that's definitely a ratio that could have come out of the cosine function, and it's definitely a ratio that you could have plugged into the inverse. So that is just your answer, and you are done. So they should be simple. It's just the ones where they try and trick you that they get a little bit complicated, okay? All right, so that's how the inverse cosine works. Next, I'll do the inverse tangent, all right? Always reach out to me and let me know if you have any questions. Good luck.